Okay, thank you. Hello, everyone. I'm Jiabin, working on the application of high-temperature superconductors, supervised by Dr. Tim Cruz. I appreciate the opportunity to be with you today. I'm here to talk to you about the project progress of our research on a wireless power transfer system using high-temperature superconducting capacitors. My presentation will be in 4 parts. We are going to look at the introduction, methods and results, progress summary, and next plans, respectively. There will be time for questions at the end of my talk. The wireless power transfer system, simply referred to WPT system, has different types. Non-resonant coupled inductors, such as transformers, work on the principle of a primary coil generating a magnetic field and a secondary coil subtending as much as possible of that field. This can happen only in a short range and often requires a magnetic core. On the other hand, the wireless power system transfer here means to transfer energy in a resonant inductive coupling way. Resonance coupling forms a tuned LC circuit. Significant power can be transmitted with the primary coil driven at a secondary side resonant frequency. Meanwhile, this type of wireless system's efficiency depends on the quality factor of the inserted resonant circuit to a large extent. Thus, high-temperature superconductors, also known as HTS coated conductors, are promising candidates for this job due to their almost zero resistance. Most relevant studies aimed at applying an HTS coil in the WPT system because it can carry significant current density and create a strong magnetic field, but few studied the effect of an HTS capacitor. Therefore, we propose that HTS coated conductors can also be fabricated to a high-quality capacitor with much lower surface resistance in HTS thin film and a larger dielectric constant in the substrate layer. Let's move on to the methods. Due to the limited access to a lab during the COVID-19, we started our research for modeling. Using the finite element method, we simulated the coils and capacitors based on the actual geometry and materials. Inductance, capacitance, and the equivalent series resistance, the so-called ESR, are calculated at high frequencies. Figures illustrate the appearance of models assembled from superconducting tapes and common materials in the software console multiphysics. Specifically, we took copper as a material of conventional coils. Meanwhile, copper is also used as electrode plates and glass is used as a dielectric. The two form a control capacitor. For comparison, HTS coated conductors were utilized to fabricate a coil and a capacitor with the same inductance and capacitance. The two tables show the calculated results of the related parameters. Obviously, the HTS coil and HTS capacitor have much smaller ESR than the conventional ones, meaning there is a much higher quality factor in the superconducting resonator. It is worth noting that I consulted our colleagues in our division who did this kind of measurement. They also agreed these figures are quite reasonable. Next, the WPT system's equivalent circuit can be simplified as shown in the top figure. Then we put the component data we just got into this system, developed in MATLAB Simulink. Figure 6 plots the voltage transfer waveforms of the system assembled by different resonators. The left half is the input voltage and the voltage on the load is on the right half. We calculated the ratio of the amplitude of the two port voltages. It is saying that while the HTS coil in the resonator has improved the efficiency from 45% to 55%, the HTS coil working with an HTS capacitor in the resonator can further increase this figure up to 70%. That is to say, an all superconducting resonator performs the best at a resonant frequency. Furthermore, we curved the transfer function expressed as a scattering parameter, namely the S parameter for different combinations in the resonator. It is very sure that the resonant inductive coupling WPT system is most effective at the resonant frequency. Also, the all superconducting resonator exhibits the highest transfer efficiency in a wide range near the resonant frequency, which is likely to benefit the tuning process of a WPT system. To summarize, we have designed the prototype of the WPT system, including a resonant circuit composed of HTS capacitors and HTS coils. Material type, geometry size, and transmission frequency are all considered. Then we have modeled all the components using the finite element method. The inductance, capacitance, and ESR at different frequencies are examined. Finally, the system model has been developed to estimate the transfer performance. The voltage transfer efficiency of different resonant materials at frequencies is calculated, verifying the significance of HTS materials. As for the next plans, the quality performance of the HTS capacitor comes to be further quantified besides the enhancement of the all superconducting resonator, consisting of an HTS capacitor and an HTS coil to the WPT system, is to be experimentally confirmed. This Gantt chart is to illustrate our progress. We hope that the pandemic will be relieved as soon as possible so that we can access the lab more often to complete the remaining experimental work. Well, this brings me to the end of my presentation. Thank you for your attention. I would be happy to answer any questions you might have. That's it.
Thank you. Thank you very much, Jiabin. So I open the floor to any questions.
Okay.
This is actually ongoing project, so Jiabin will continue till next year, till next few months.
Okay, sure.
Yeah, one quick question, if I may.
Okay.
Thanks, Jiabin. You mentioned high temperature, but what kind of temperature would there be for the power transfer?
In the liquid nitrogen,
300 Kelvin or sorry?
In 77 K in the liquid nitrogen bus.
Okay, 77, not 300.
Yeah, not 300. Yes.
Yeah, thanks. That's helpful.
Thank you.
Thank you. Any more questions? If not, then we would like to thank the speakers. Thank you, Jiabin. There will be another presentation in June, the final one, so we would be able to ask more if you're interested.